Let's consider the function f of xy equal yi plus xj. A graph of some of the vectors depicted or defined by this function might look something like this. And let's just explain briefly. Let's consider this point here. Y is this big, x is only this big, so that the I component being equal to the y vector, and I think I said that backwards, the x component is this big, the y component is much smaller. So the y component of the vector that we get here, the y coordinate of the vector that we get here is going to give us the I component, which will be smaller than the j component, which is given by the larger x value. So the vector will be bigger in the j direction than in the I direction. For this point, the y coordinate and the x coordinate are both positive, but the the x coordinate is now smaller, which is going to make the j component of this vector smaller. The y coordinate is bigger, making the I component bigger. You might want to make a table of values and see how this works. Now, if you there are symmetries and so forth. For example, if you replace y and x by their negatives, it's going to reverse the direction of the vector, so that, for example, if we reflected this point over to about here, the vector would come down kind of like this. And we see that as we move around, let's say, this path, which is sort of a circle, what's the orientation of these vectors with respect to the path? If we move around this path in the counterclockwise direction, then here the vector has a component in the direction of the path. Here the vector has a component in the direction opposite to motion along that path. In other words, if we have a velocity vector along here, and this would not be the acceleration vector, this is a completely different vector, this is our vector field, this vector has a direction in the component in the direction of motion. This vector has a negative component in the direction of motion, as does this one. But by the time we're down here again, we're at a positive component, and that remains here and here. But by the time we get over here, the component would be negative, and then by the time we're here, the component in the direction of motion is positive. So that's going to give us some insight into how the curl behaves, but the curl appears to go positive in some places, negative in others, and there's a certain symmetry to that. So we might expect that the curl's not very big. The positives could balance out the negatives. The divergence, well, as we move in, say, to the origin, if we move into a much smaller circle, the vectors get correspondingly smaller because our x and y values get correspondingly small. If we move in 10 times as close, then the vectors are 1/10 as big, and they still have directions that aren't radial. This one is directed outward from the curve, this one's directed outward, but now this one's directed inward, and this one's directed inward. Then these are directed outward, but these are directed inward, so that if we were to look at the net outflow from this point, it might well be 0. Now the divergence of the function is associated with outflow. The curl of the function is associated with alignment, basically in the direction of motion around a curve. And for now, we can think of that as motion around a circle. So let's see. Gradient of f is del dot f, which is partial with respect to x, I, plus partial with respect to y, j, plus partial with respect to z, k, dotted with yi plus xj. The x component of y is 0, and the y component, or the x derivative of y is 0, the y derivative of x is 0. There is no k component, so that the divergence of f in this case is 0. What about the curl? Well, that's del cross f, which equals the determinant I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, and here we have y, here we have x, here we have 0. Now the I component is going to be partial with respect to I of 0, partial with respect to z of x, and that's going to be 0. So we're going to have 0 times I. And then we're going to have minus j times partial with respect to z of y, which is 0, partial with respect to x of 0 is 0. So that's going to be 0j. What about the k component? Okay, well, that's going to be partial with respect to x of x, which is 1. Partial with respect to y of y is 1, but it's this minus this, so that's 1 minus 1 times k, which is the 0 vector. Now, what if we change the signs of either the y or the x? That wouldn't have any effect on the divergence, but it would have an effect on the curl. If we change just one of these signs, then the sign of one of these derivatives is going to change, which is going to give us either a negative 2k or a plus 2k. So let's ask, what's the curl of the function, let's say negative yi plus xj. Now the components are the same as they were here, except the y is going to become negative, and since we're subtracting the partial with respect to y of y when we do the k, that's going to give us a negative, minus a negative 1. So without writing this out, I'm going to assert that this curl equals 2k. The curl is no longer 0. Now if we look at the graph of our vector function, and if we think of graphing this function, we can do that, excuse me, we could do that independently. Lots of ways to construct that graph, but what I want to do is just go around this circle and look at what happens to the directions of these vectors. Now, if we change the y coordinate and make it negative, what's that going to do? That's going to reverse all of our I coordinates. It's going to reverse the I coordinate for each of these vectors. So that a vector in this direction is going to reverse I coordinates and go in this direction. This vector will reverse I coordinates and go in this direction. So that what we're going to have is, okay, this vector, which was here, is going to reverse its I coordinate. It's now going to be in this direction. This vector is going to reverse its I coordinate. So instead of being out here, it's going to be in this direction. This vector will reverse its I coordinate, which will take it over in this direction. The j coordinate will still be equal to the x value, which is negative here, but that's going to change the vector in this manner. And if we go around the rest of the circle, okay, reverse the I coordinate here, it's going to take it over this way. Reverse the I coordinate here, it's going to take it in this direction. Reverse the I coordinate here, it'll take us in this direction. Reverse the I coordinate here, it'll take us in this direction. So if we were to move in this circle around the origin, we would see that these vectors all have substantial components in the direction of motion. And in fact, though we can't tell it for sure from a rough sketch, this reversal will actually make all these vectors tangent to this circle, giving us a maximal possible curl for the magnitude of the vector, rather giving us a maximal integral around the circle for a given magnitude of the vector. Now that's something you would maybe want to prove for yourself, but it illustrates, first of all, calculation of divergence and curl, and second, how the alignment of the vector field can affect the divergence or the curl. Now, just to emphasize the fact that this field doesn't diverge, in this case we can simply sketch shorter vectors. Actually, that sketch isn't working out, but these vectors get much smaller as we move in toward the origin, but they don't have any particular alignment with the radial direction. The alignment with the radial direction keeps changing as we move around this region, and you can make a similar statement here. So the divergence in both cases is 0. The curl in this case is 0. The curl in this case is non-zero. We have a circulation around the origin. And in fact, that's not confined to the origin. This result doesn't depend at all on the value of x and y, so that wherever we are in the plane, we're still going to end up with the same value.